Bismillahirrahmanirrahim. Assalamu alaikum. I'm Arzu Hassan, CAO Power Pakistan. Welcome to Spring STEM Lecture Series 2021. Today we have with us a very ambitious, bright and young research scientist, Dr. Zafar Said. Thank you so much, sir, for joining us. Dr. Zafar Said is currently working as an assistant professor in University of Sharjah. Previously, he worked as a postdoc fellow researcher in the iSmart group in Department of Engineering System and Management, Masdar Institute, U.A.E. He completed his Ph.D. from the University of Malaya, Malaysia. He has graduated with a BS in Mechanical Engineering honors from University Tenaga Nasional, Malaysia. He also serves as the coordinator of the Functional Nanomaterial Synthesis Lab, RISE. Dr. Zafar is a part of the Sustainable Energy Development Research Group and is a Functional Material Research Group member within the Center for Advanced Material Research Center and a researcher in RISE. His research achievements include about 100 research papers, 2 books and book chapters, 18 conference papers, with about 2870 citations and an H index of 30. He secured more than 2 million AED in research grants. He was honored with several prestigious awards, including among many, Sharjah Islamic Bank Award for Distinguished Researcher 2017-18, Faculty and Annual Incentive Research Award for 2018-19. His research interests are in the base areas of renewable energy, heat transfer, nanofluid, supercapacitor, underhood thermal management, and active thermography. Welcome to the platform of Power Pakistan, sir. I hope that we will have a super informative session with you today. Over to you, sir.
Thank you. Thank you for having me. What I'll be delivering today is thermophysical properties of nanofluids and application. So I'll just go on overview from what are nanoparticles, what are nanofluids, why is the need for them. I'll touch on some application in different fields. Maybe anyone who is interested in those areas could catch up why this nanofluids are important for them, or how could this help them in doing their research or doing their master, PhD, or further studies. So let me do it as a full screen. So I believe now it's okay, right? So here's my email, zaid@sharjah.ac.ae, in case you guys need it. Okay, it's giving me subtitles. Do you need those? Anyway, let's see. So the outline that I'll be covering is going to be the background, application of nanofluids, and then the preparation of nanofluids, thermophysical properties, experimental studies, their limitation. Then we'll look into some of the future challenges. And by the end, you'll have, of course, your question and answer sessions. Now, for example, someone could ask, why do we need nanotechnology, for example, or why do we need new technologies or new developments or new breakthroughs? So we all know things are getting faster. So the heat rejection requirements, for example, is continuously increasing due to the trends towards faster speeds, like your computers, your phones, your cameras, anything, name them. So the problem is, yes, we are getting faster, but we also, what happens is in these microelectronic devices or engines or bright beams for optical devices, they start to get heat up. So now how do we cool them down? So conventionally, the heat flux rates are what we do basically in the olden days, or even now, we extend the surfaces such as fins and microchannels, and we also can increase the flow rates. But these two, yes, have already reached their limitation, and yes, increasing the flow rate also increases the pumping power. So everything that we do has a catch. Now, however, current design solution already are pushed to their available technology to its limit. So this is the reason why nanotechnology started. Nanotechnology, basically the word nano comes from 10 raised to minus 9 meters. So basically nanoparticle at that dimension, that 10 raised to minus 9 or even smaller, or even 10 raised to minus 8. So dimension that are at the nano level. Now, If to simply explain to you guys nanofluids, before it was not very common, but now I think a large group of scientific committee or researchers are working in the area of nanofluids for various applications. So easy example will be if you take a spoon of sugar, you add it in water, yeah. So what happens is you get a very good mixture of your tea that you have, for example, the red tea or the green tea. The idea of nanofluid is we want to have our fluid similar to how what we do the tea, but without having any agglomerates or without having any suspension or the sugar particles that are not mixed and they stay at the end. We don't want that. An ideal nanofluid is to have it fully suspended within the liquid and become a part of the liquid so that you do not have any stability issues at the end. Now, in generic application of nanofluids, these are just a basic image. It could be used in defect sensors. It can be used for anti-infection therapy. It can be used for energy harvesting system. Nowadays, the nanoparticles, for example, are being used in cancer treatment. You have them for tumors. I mean, various applications. It's also used in cosmetic. My area mainly is the energy harvesting system and the heat transfer, which is here between different solar collectors, shell and tube heat exchangers, microelectronic devices, heat sinks. So this is my main area. But anyway, I'll show you some basic application. So here, most of the figures, for example, this and this are my studies that I started with in my PhD. So we use nanofluids in order to enhance the overall heat transfer coefficient. We studied in detail the energy and exergy efficiencies. We found that using nanofluid enhances the efficiency of varying solar collector. Then, of course, people first they were trying metal oxides because they're cheaper. Then graphene came into being. People started working on graphene aggressively and they did a lot of research. But the one issue is again the cost in here. The better the thermal conductivity, better the properties, sometimes the cost is higher for those nanoparticles. So this is one of the challenges that we'll talk later in on the cost. So yes, you can take nanoparticles such as graphene, for example, which has better properties, but the more amount of graphene you use, we know how expensive it is, or still making large sum of graphene with good quality or good with less impurities is not easy. The second application is that the thermal conductivity as well as the heat transfer coefficient is higher in nanofluids than the base fluid, because for example, later I'll be showing how is the comparison between the liquid and the nanoparticles. The base fluid, and so it has a great application in industrial cooling application. For example, this one, we tried to use it in a Toyota Corolla radiator. This is for a 1.6 engine car. We saw that using ethylene glycol water mixture with aluminum separately and titanium oxide TiO2 nanoparticles separately, we saw that the effectiveness increases, the efficiency increases, the Nusselt number increases. Of course, it's directly related to the flow rate. So using nanofluids in such system could enhance the overall performance, as well as it could also result in reducing the size of these heat exchangers. Because someone could ask, why do we need to reduce the size of this radiator, for example? The reason is why the less smaller the size, less is going to be the weight and better is going to be your efficiency. So those are one reasons why someone aims to enhance the heat transfer. Another area is the smart fluids. So a particular class of nanofluids can be used as smart materials working as a heat wall. So an easy example I'll give you, for example, magnetic nanoparticles. If you use them in the water and without applying the magnetic field, they will be suspended and they will be doing their job of heat transfer. However, if you apply a magnetic field, you can use them as valve to control flows or to, and this nanoparticles also, for example, graphene modified with oleic acid has been proven to show improved friction and anti-wear performance. Similar, nowadays we have a new group that is coming up, and a lot of work is coming out, especially from my group, my supervisor, Dr. Prof. Saidur, and other colleagues on Maxine. So Maxine also, there are about 70 different phases and only about 20 are explored, but for nanofluids, not many. So a large potential area that could be expanded. Nuclear reactors. This is also an area where what nanofluids can be used for cooling the nuclear reactors. So what we did, we started a couple of papers. So possible application for the PWR, that is the primary coolant, standby safety system, accelerator targets, plasma diverters, and so forth. So we investigated aluminium, Al2O3, TiO2, CNT with water-based. So we made water-based nanofluids, and we found that using nanoparticle actually enhances the efficiency and it does not have any negative impact, which is actually a good potential. Now, the second study that we are currently doing is to see the effect with rising temperature, because when you're increasing the temperature or the changes in pressure, we want to see the stability of these nanofluids. So for that case, we are considering the multi-wall carbon nanotube because we know they can withstand high pressure and temperatures. But the idea is to see when we increase temperature high and then back and forth to see if there is a hysteresis loop or not. The other example that people are now doing, and I know a group of my friends who are from Malaysia, they're actually working on the lubricant using nanoparticle with graphene, and it is in the final stages. So hopefully they will be having the lubricant, a graphene-based lubricant used in the engines. So it has been already shown in several studies that using nanoparticle can enhance the fuel efficiency. It can enhance the, for example, reduce the emission rates of the air pollutants and other greenhouse gases. And it can also reduce the exhaust gases overall. So overall, using nanoparticle in your fuel enhances the property. Another thing is the microchips. The faster we become, the smaller we are going. For example, the Apple nowadays has a processor of 5 nanometer. Previously, they had 7 nanometer, and they're targeting to go even smaller and smaller in order to increase the speed. But when this happens, we know there is a high amount of heat being generated. So how do we get rid of them? So nanofluids could be used as the cooling fluids around these chips. For example, you would have seen supercomputers, they're cooled with coolants, and these coolants could have nanoparticles for better efficiency. Another area, which is the nanofluid in drug delivery. This is a group that I joined recently. So we came up with a group that is between engineering and medical. So we are trying to work on different nanoparticles for drug deliveries and for several treatments such as cancer, tumors. So we have started working on that. Of course, it's not my area, but my expertise are with the nanoparticle characterization synthesis and seeing the because even in the drug delivery, the stability is very important. So I do have those expertise, and we are trying to explore different areas. And clearly you can see here already, this was a paper back in 2012. Now if you see, there are a lot of advances. One very good example is the cell membrane. If you try to see the pictures, you cannot see them clearly, but using, for example, FeO nanoparticles, you can have a high contrast of the images. Another way is putting, for example, the gold or silver nanoparticles. So if you put AU nanoparticles, they go to the cancerous cell. They basically are targeted in a way that they go around the cancerous cells. Once you send in the radiation or the laser sources, they will be killing those infected cells. So this is another application. Well, there are a lot. You can see several. Nanofluid for sensing application. These are also some studies that people are doing, that even for very minute traces of cation in industry environmental sample can be detected using different kind of nanoparticles, of course with the solution that they're mixed in. So okay, these are some of the application. Of course, there are many that I left out. I did not mention them. So what is nanofluid? These are some of the samples. You can see them clearly. Basically, we have the water. I worked extensively with water. Now I'm working with ethylene glycol and water-based nanofluids. And eventually, we are trying to move towards ionic liquids as well as the PCMs and molten high-end oil, for example, for high temperatures. Because the low temperature range nowadays for nanofluid is becoming saturated. The high temperature is something that is lagging, and not many studies are there. So nanofluids are basically dilute liquid suspension of nanoparticle with at least one of their principal dimensions smaller than 100 nanometer. This is an example. These are carbon nanofibers that we prepared in our lab, suspended in water. You can see clearly it aggregates. There is no stability, or it's very bad in terms of stability. This is graphene oxide. Everyone knows when you suspend it in water, it stays stable. This is functionalized carbon nanofibers. The same carbon nanofiber, we functionalize them using the HCl and H2SO4. So what happens is it stays suspended. And if we take a mixture which is a hybrid of these two, we found that the stability is lower compared to graphene and FCNF. So these are some of the challenges that still people are working on to find out in order to get nanofluids that are stable for long term. Here is just one of the figure showing you the number of papers that are published in ionic based liquids, in hybrid. Hybrid is increasing gradually from since 2011. Nanofluids, you can see how high, and the number of publication per year are now for 2020 and 2021, I would say it will cross even 4,000 papers. This is a schematic diagram of the whole process of nanoparticles. So the nanoparticles could be 0D, 1D, 2D, or bulk or 3D, and it could be polymers attached as surfactants or polymer-based nanoparticles. What we do is we take the water, any of these as a base fluid. It could be anything, not only water. You mix them. There are different techniques: one single step, two-step methods, and you prepare the nanofluids. Then these nanofluids, of course, can be used for varying application, and we have to see what is its impact and study them. Earlier, people just saw the heat transfer concept, but now with time, people are looking into economic impact, environmental impact, into cost analysis, into payback period, in order to make or convince the industry that yes, these things are working, they are giving the properties, and they should be moved now to the industrial scale, and investment should be made in that area. This is one of the paper we did on nanofluids only for solar collectors in detail in terms of energy, exergy, economic analysis, and environmental impact. In progress in energy and combustion science. I mean, I know publishing in high impact in terms of material and energy storage and batteries, and if you do good work, is easy to do. But publishing in the area of nanofluids with high impact journals without doing the proper science and physics background in it is not that easy. So materials of nanoparticles and base fluids in here, like we said, nanofluid is the base fluid. It could be water, oil, ethylene glycol, or biofuels. The nanoparticle could be metals, non-metals, metal carbides, and oxide metals. This is the main key why people want to suspend nanoparticles in the base fluid. So you can see the thermal conductivity of water, for example, it is about 0.613. Here you can see it is the ethanol, which is 0.171. Methanol 0.2, and everything you can say below 0.2 and onwards. So of course, now these base fluids, if they're used for heat transfer application, they're going to be bad in terms of thermal conductivity. So what you do is, for example, let's take a diamond or carbon nanotube. We take a little or a low volume fraction of this, we suspend it in this. So by basic math, we know adding the thermal conductivity of this and taking this as a mixture, we know it will enhance it a bit. Maybe yes, the enhancement might not be in 100%, 200%, but it could be 20, 30, 40%. Because the other idea is we cannot also take large amount of solid particle and suspend it in the base fluid, because that would result in negative impacts such as pumping power, pressure drop, and also it will not be a liquid anymore. It might be an emulsion. The preparation of the nanofluids, there are generic two steps like I discussed earlier. So there is one step method in which the production of nanoparticle and dispersion in the base fluid are done simultaneously. An example is here, the graphene, you put it and you get reduced graphene oxide. This is the one step method. You have direct evaporation technique for preparing it, chemical reduction, laser ebullition, microwave irradiation, and phase transfer method. The most common method, or the reason will be the cheap method, is the two-step method where the nanoparticles are produced first and then dispersed into the liquid. So you have the liquid, you put the nanoparticle, you use prop sonication, microfluidic, or different methods for mixing in order to make sure that the nanoparticles are suspended. Now, after you have the nanoparticles prepared by the one-step or two-step methods, what is the next issue? The issue is when we put these nanoparticles within the base fluid, we might see aggregation. The aggregation could be due to agglomerates, which is held by weak van der Waals forces, or it could be due to aggregates, which is held by strong chemical bonds. So the main idea is we want to make sure that the best ideal case is to have each nanoparticle suspended alone. But that does not happen. Usually you'll have two or three particles coming together when you suspend them in a fluid. And then we have different techniques of seeing if these nanoparticles, what are the size after we suspend them in the liquid. In powder, we know the size, but when we suspend it as a nanoparticle in a liquid as a suspension, what is the sizes? So we use the zeta potential, for example, to get the hydrodynamic diameter. So what do you see is you get the size of the cluster of these nanoparticles which have come close together, and this is the size that you get. So you don't see the size of one particle anymore. It is, for example, 6 or 7 together, and that's the reason why when you see the size of the nanoparticle in a fluid through TM or other thing, you will see that if the size was 10 nanometer, the current size will be 80, 90, or even above 100. That is because still we have two challenges of the stability. These aggregation or dispersion of nanofluids, or these issues could be due to physical stability or chemical stability. So in physical, the failure modes are aggregation or agglomeration, which we already talked, due to weak van der Waal or chemical bonds. Then what happens is you have surface deposition, and once they come together, of course, the density becomes higher, and eventually they will sediment. The second one is the chemical stability. Failure modes, it could particle could get oxidized, the base fluid could oxidize. You could have coalescence, means two coming together forming a larger particle. You could have sintering. You could have morphological transformation. You could have dissolution. You could have oxidative etching, coating detachment, or fragmentation. So these are all the challenges that still are there for the varying different nanoparticles. Because see what people are doing, especially the long time, even me, for example, I'm from mechanical background, so all my interest is to see the heat transfer, the energy, exergy efficiency, and how does that work. But the idea is to when you suspend the nanoparticle in the base fluid, we need to know what is the physics and chemistry behind it. If we don't know that with time, yes, I might make a very good nanofluid with high properties and everything, but that might be on the first week of preparation. What happens if I look after 6 months, after 3 months? Do the properties stay the same or no? Does the nanoparticle aggregates or no? Is this suspension stable or no? So these are very important, or the question that actually the industry is interested in. So in stability, one of the method that we check the if nanofluid prepared is stable or no is through the zeta potential in the millivolts. So if we have anything above plus minus 60 millivolt, it is extremely highly stable. It means even for 6 months or even more than a year, you're not going to see any aggregates or any sedimentation. However, if you're in the range between 40 to plus or minus 40 to plus or minus 60, you are within the range of good stability with low settling or moderate stability. Anything below plus or minus 30, it means that with time you're going to have sedimentation. So this thing, of course, with science and walls, people do work and you find out. So what people did is they started using surfactants, for example. So you can see here graphene suspended in water, it sediments right away and it has a low stability. However, when you add a surfactant, you have a good high stability, probably more than plus or minus 60 millivolt. But then another question comes in here, which is again a challenge and limitation that will come and be discussed later, but I can mention it here itself. Now, some surfactants, they have low boiling, for example, boiling points. Assume the surfactant that you use is Arabic gum for the nanofluid, and you're going to use this nanofluid, for example, oil based, it's not water based, and you're going to use it for temperatures above 200 or 300 degrees Celsius. What happens to this surfactant is, for example, if it's Arabic gum, it has a melting temperature of 80 degrees Celsius. Once you cross that, it will move itself out of the nanoparticle. The nanoparticles are going to sediment, and this once on cooling down, it is going to form a cluster itself, the Arabic nanoparticle coming together, and it can actually clog your systems rather than giving you positive result. This we tried in one of the evacuated tube solar collectors where the temperature goes beyond 100. So we use Arabic gums with the multi-wall. We found out that with time, once it cools down, it actually clogs the system. Just while it's hot, it keeps working. But once it's cooled down, the Arabic gum ends up clogging the system and forming larger particles rather than smaller ones. Now, stability of nanofluids. These are this is one of the paper you can look at. Of course, there are other papers nowadays, and even our paper that we published. So it discusses in detail the causes of instability, which is the Brownian motion, particle size, type of nanoparticle and base fluid. Sonication time is also important. Particle-particle and particle fluid interaction, and thermophoresis. Then what are the enhancement techniques? Like I discussed, addition of surfactants, surface modification techniques, which is functionalizing. I believe functionalizing is one of the best methods to do compared to surfactants. pH control is also there, but assume your pH control, maybe it's pH 3. That's not good for your system in terms of heat transfer. Then ultrasonic agitation. Then in stability enhancement mechanism, it could be less van der Waal attractive forces, high electrical double layer repulsive forces, higher adsorption of ions, dissociation of surface charged species, isomorphic substitution of ions, accumulation of electrons on the surface. And lastly, how do we evaluate them? Sedimentation and centrifugation method, zeta potential method, spectral absorbency analysis, and 3 omega method. Now we are done with the stability discussion. Of course, there is a lot to discuss, but I'm just giving a brief overview on that. What happens when we put the nanoparticle in the base fluid? It results in increasing the convective heat transfer coefficient, thermal diffusivity, viscosity, and also thermal conductivity. Now, there are some properties which, when enhanced, are good for us. There are some which, when enhanced, for example, viscosity is not good for us. So let's look into these in detail. The concept of the Brownian motion or the enhanced heat thermal conductivity that we get in the base fluid is the Brownian motion, which is the key mechanism controlling the thermal behavior of nanoparticle fluid suspension. The second reason is the interfacial layer, which is the nano layer, that is the liquid molecules close to the solid particle surface form layered structures, such as this. You have the nanoparticles on the liquid surface. These layered structures act as thermal bridges between one side to the other. So, of course, it results in better heat transfer between the nanoparticles and bulk liquid, and it enhances the thermal conductivity. As an example, is this is the particle initially. After some time, here is the particle, so it keeps going back and front, it keeps bouncing the other particles or molecules, and this results in higher heat transfer. So there are basically 4 modes of energy transport in nanofluids. Mode 1, mode 2, mode 3, and mode 4 is not shown in here. So you can see the water molecules around the nanoparticles in here. So the first mode is the collision between the base fluid molecules. So the base fluid and base fluid molecule collide. The second mode is the thermal diffusion in nanoparticles that are suspended in this fluid. The third mode is the collision between the nanoparticles and nanoparticles. So one nanoparticle to another nanoparticle. And the fourth mode is the thermal interaction of dynamic or dancing nanoparticles with the base fluid or the base molecules. Now, thermal conductivity, which is one of the key, or you can say the selling point for nanofluids, but with time, people found out it's not just taking the nanoparticle and suspending it in the base fluid and you have high heat transfer. There are a lot of parameters that needs to be taken into account if you want to have a very good effective thermal conductivity. One of them is the nanoparticle size. Second is the nanoparticle shape, nanoparticle thermal conductivity, nanoparticle concentration, operating temperature, base fluid properties, thermal conductivity measurement methods. Maybe you take the same nanofluid and measure it with 2 different techniques, you might get different values. Nanoparticle stabilization techniques. So here also there is a challenge right away. I'll discuss it here. No need to discuss it later. So knowing that in future we need properties, the formulas or equation that could predict the effective thermal conductivity. But for it to do, it needs to take all these into account, which means it is not very easy, at least for the time being, to come up with an equation that can be used for all sizes and all shapes of nanoparticles. So this is also a gap that needs to be developed to come up with a universal correlation for different nanoparticles. The second thing is the thermal diffusivity, which is meters square per second. So of course, if K is increasing, thermal diffusivity will also increase. So it is the measure of the ability of a material to conduct thermal energy relative to its ability to store thermal energy. Change in specific heat. So specific heat, definitely if you're increasing the thermal conductivity, the specific heat is going to drop. But in some cases, we want it to drop, in some we don't. So let's look at this figure in here. For example, this is the change in specific heat. So already studies have proved or shown that if you add nanoparticles in the base fluid, no matter what is the concentration, it is always going to reduce the specific heat. If you do the same for base fluids such as ethylene glycol water mixture, the same case, it's going to reduce the specific heat maybe up to 15 or 20%. However, if you use ionic liquids, studies have shown that it could increase the specific heat. or it could also decrease. And for the molten salt, which is the area where we could use in, like I said, a new area where using nanoparticle can help with better properties, such as also the specific heat, which means it will also result in improving your storage. Now, change in viscosity, just like the nano thermal conductivity, viscosity also has various parameters that needs to be taken into account. So it's the morphology, the shear rate, temperature, volume concentration. And we know if you're adding nanoparticles, solid nanoparticles into liquid, it is going to increase the viscosity. But in some cases, it proves to be positive, in some negative. But if you compare the overall enhancement of thermal conductivity with the viscosity, thermal is higher. So usually this is neglected. Now, the change in density, just similar to the viscosity, increasing the adding solid nanoparticles would result in increasing the overall density of the nanofluid. This is one of the equation we propose, which takes both the temperature, volume, concentration, and density of base fluid and particle into account. And we compared it with various models, and we saw that our model, the proposed model, gives much more better results compared to the experimental study versus that of Park and Cho. Now we come to the applications. In the application, there are various applications. I'll just discuss the ones that I'm working on. So one of them is, for example, studying the thermophysical properties of nanofluid and implementing it in a heat pipe. Of course, using maybe both inserts as well as nanofluids. So like I discussed earlier, you can increase the heat transfer surface area, such as fins and these. So what we do is we add inserts, tape inserts, and along with nanofluid, and we compare the overall heat transfer. So you can see here thermal conductivity is one with different volume fraction and temperature, viscosity with temperature and volume fraction, specific heat, you can see here there is a reduction but not much. Density, you see it increases, but of course it follows the same trend as of that of the base fluid. The Nusselt number you would see in here for different Reynolds number. So the best result I would say is for the yellow one with 0.2, and when you have the tape configuration of 95 mm. So you can see the results are higher. So combining both techniques of the tapes as well as the nanoparticle in with the base fluid would result in increasing your Nusselt number, which means it's going to increase the overall heat transfer. Another application is if you take, for example, hybrid graphene with other nanoparticles. Of course, it's good for, it gives better thermophysical properties. We used it in a LFR, linear Fresnel solar collector, and we saw that the entropy generation, of course, it reduces. You can see clearly from this point to this point. The Nusselt number, there is an enhancement with the volume concentration. And the thermal efficiency, it's obvious, higher the volume concentration, better is the overall thermal efficiency compared to that of water. But you can see from 0.3 it increases to 0.32. So again, it doesn't mean that if you add nanoparticle you will get 100% the efficiency. Another solar collector that we tested using the multi-wall carbon nanotubes with Arabic gum is the PTC system, parabolic trough solar collector. And now this was only with nanofluids. Currently, we are doing our studies, we are doing different inserts, fins with nanofluids to see what is the overall efficiency. Of course, for every study that we do the nanoparticle, the preparation, the properties, and then the system. Here we have another study of a flat plate solar collector. What we did in here is we combined nanodiamond nanofluids with different concentrations. And what we saw is if you use nanofluids, it results in reducing the overall collector area. It means higher the volume fraction, higher is the overall efficiency, which results in increasing the overall performance. Therefore, it could give you the room to reduce the collector area by at least this much. So you can see from 2 to 3 meters, or about by 1 meter square, you can reduce this. The same study we combined with inserts, core rods, and nanofluids, and we saw that the enhancement is even further, and it can reduce the area even way better compared to that when you only use nanofluids, and overall heat transfer is increased. Now, this is another, the carbon nanofibers that we did, the CNF versus the functionalized. You can clearly see CNF is long, functionalized is smaller in size. So smaller in size resulted in better stability as well as better heat transfer compared to these. But friends, what we found out when we were done with the final study is this FCNF is stable even for more than 2 years. This one, it is stable when you prepare it, but after 1 day, I would say it completely sediments, even though the properties when you prepare them initially are the same. And we tried to correlate these properties from the nanofluids to see how it would affect in the storage, for example, supercapacitors. So we found out when your thermal conductivity is very high, this one is not going to be a good storage material, but it is good for heat transfer but not for storage. This one, however, would result in better storage compared to the FCNF. So this could also be, there is a study that we are still working, trying to figure out if how can we correlate right away the nanofluid properties and see how does it affect in terms of storage, or which material is better for storage. Now we come to the limitation and challenges. Like I already discussed, one of them is stability and the different ways that we have to look at. Second is predicting the correlation. So we need something, a universal correlation. Then higher production cost, but there is a bit of good news. With time, more industries are getting into preparing nanoparticles. So the things that were let's say $1,000 per gram graphene used to be, now it is even cheaper. The same multi-wall carbon nanotube, if you get industrial grade easily, now you can find 1 kg at the cost of $400. So think the costs are coming down. So this is one of the challenge which will be addressed soon. Pumping power, not much, but yes, there are sometimes challenges if you use high volume fraction of the nanoparticle. This is the thing that is happening nowadays, which is the form formation. So for example, when the nanofluid gets heated too much, and if you use a surfactant or something, it would result in form formation. Another thing, or the challenge that still needs to be addressed, is to come up with practical industrial application. It means to move from the lab scale now, and from the lab scale to industrial scale. So this is one of the challenges that we are fluid for as transformer oils, then using 2D materials such as MXene and others to explore their properties, and then also to look for better preparation steps and standardization techniques. Another area that is not being explored much, we only did a couple of studies to look into the mechanical erosion and chemical corrosion caused by these nanofluid with time. Another area or a gap is the disposal. Once you're done with these nanofluids, where do they go? Where are they disposed? What is its effect on environment and life cycle? This is also an area which has not been done much yet. Why? Because we don't have the people from that specialization working into this. This is just present and future direction. Basically, we are currently somewhere here in the hybrid nanofluids. Now more work needs to be done towards these, testing different type of base fluids, different type of nanoparticles. And in future, we see from hybrid nanofluids, we are going to move towards pico, then hybrid pico, hybrid fluids, hybrid pico fluid, which means there is a lot of research gap that still needs to be filled. And the smaller the size, the better we are going to have, or we are going to see the properties. So that's all. If you guys have any question and answer, I'm here to answer them. And thank you for having me again. So please, the floor is open for you.
Thank you so much, sir, for the wonderful presentation. Every time I would think of a question, you would answer it in the next slide. So I couldn't come up with a question. If someone has any question, please raise your hand, or you can just unmute yourself.
Or is it that I was running too fast and people couldn't catch up?
No, no, no. The lecture was amazing, I would say. So considering the stability of the nanofluids, it takes you about 6 months, as you mentioned. So how long does it take you to complete one project?
See, the main issue that we face nowadays with time, people are learning, they're becoming experts in this thing. So preparing a nanofluid would not take you much time, but preparing a new nanoparticle would take you time. And then once you take this new nanoparticles, for example, hybrid nowadays, I take nanoparticle A and nanoparticle B, I mix them. Okay, I get good properties. But then the issue comes is when you put it in the base fluid, you need to know the science or the chemistry behind it, that how is it going to be stable in that liquid. So that is the main challenge. So if you don't have anyone with the background from nanomaterial or nanotechnology or chemistry or physics who cannot select the known nanoparticle for the known base fluid, you're going to face issues. So we as people from mechanical background, what we do is we do trial and error method, and we test them due to the different system, and once we get lucky, after that you just take mass up the nanofluids and then you use it for heat transfer. If you're doing indoor control experiments, it doesn't take you much time. However, if you're doing, for example, solar collectors or solar system or things that deal with nature or weather, well, sometimes it even takes you 1 to 2 years, because if your system is not good, your radiation is not good, you face issue of stability, you face issue of clogging. So yes, there are a lot of challenges that comes along with the experimental work. However, with the lab section preparing, taking properties, now things have become faster compared to before.
All right. So
Yeah.
there is
Good
another
afternoon, sir.
question. There is a question from Faiza Sayed.
Yeah,
Are there
Faiza, please.
functional nanofluids being used for cooling personal computers?
People are already doing, so if you see, there are already some studies where they're using nanofluids for cooling PCs. So yes, it has an application and you will find them in some of the fancy PCs. But my idea is still, what I'm trying to say is we are still struggling to convince the industry or to come up with the industry or to bring the industry to invest in this, because you know how industry is, they want to be sure that whatever we do, we get the money out of it. So currently I'm working with several industries. One of them hopefully will be getting, if we get lucky, we'll get the fund, and we are going to try it for the chiller systems for district cooling using nano refrigerants and nano lubricants. So if that happens, probably we'll be one of the first groups that is using it in on industrial scale and actually implementing it in industry. So that is the thing that is lagging. And like my colleagues who are working in Malaysia, they're using the nano lubricants within the car engines, and they're in the final stages of register. They have already registered the product, so once it's done, they will start doing it commercializing. So this is what is still lagging. Once we hit that, that is what the objective of research should be, because with time you will realize that it's not just publishing papers and publishing papers. Yes, we do that in order, you would know that publish or perish, the thing is that, but you also need to know that if you do something or you work something, does it has an impact in terms of industry, in terms of a product. So that is the key thing in that. So if you keep on doing a research for years and years and years, and it has no impact on the as a product or as a on the general environment or on the general public, then I would say, at least I think, that research will not be useful. It's just useful for you in terms of papers, but not as a product.
Another important factor is the cost effectiveness. So where do you see it?
That's what I said in earlier days when we were doing. I think I started working on nanofluids from my bachelor's. So earlier days, I would say I worked on single wall carbon nanotubes. I got it from States. It was 100 grams, and I paid $9,000. But now, if you do the same, I think probably industrial grade single wall carbon nanotube, you will not be paying $1,000, or if not 1,000, at least I'll say it has dropped by 10 times the cost. And the same, the multi wall carbon nanotube. Now you guys, like, we are using it already. So we took industrial grade 1 kg, which cost us $350. So it means per gram it is even lower than, just like how the solar energy, the PV cell and PV technology became cheaper, this will also become cheaper. The more the industries are there who are preparing these nanoparticle in mass amounts, the cheaper it will get. And yes, that challenge is pretty much answered. Only now the next challenge will be, like, it's not a challenge, industries are already looking into it, into how to prepare large amount. Like, for example, assume if we want to work it in a district cooling, and we want to use a nano refrigerant, we have to come up with a method of producing large amounts. So that could be a challenge.
All right, there is another question. Have you used nanofluids for drug delivery?
Yeah, people are using, and like I said, I joined a group recently. So what we are doing is we are taking silicon nanoparticles, We are trying to use, of course, the polymerization and everything, because inside the human body you have the receptors and receivers, so you need to design the protein or whatever on top of these nanoparticle for that functions. And yes, they are being used already in drug delivery, and if you look on Google Scholar, you'll find thousands and thousands of papers. And another way, it could also be injected into your blood for several application. I'm not an expert in that side, but yes, it is already being used. Gold nanoparticle, a lot of work has been done on that.
And a final question from my side, taking advantage of your presence today. So you're running a research group, right?
Yes.
So are you open to take any more students for your research group if someone shows interest after today's lecture?
Yes, sure. What I do basically is, see, for example, if we have any openings, we invite people to, of course, send their CVs. And when there is anything, we tell them to, of course, participate in it. And of course, they are shortlisted, they can join. If that doesn't happen, what I do is I actively work with students from India, Pakistan, Bangladesh, whoever is interested. I don't have any, what they say, selection. So what we do is I try to train them on working research papers on topics that could be done remotely. So maybe, or even experimental, if I could guide the person and the person could do those experimental studies and data within his station, that could be done. We could work on hot topics such as review, we could work on numerical papers, numerical studies. So yes, I'm open for collaboration, and if anyone is interested, please send me an email. Yeah,
Thank you so much.
you're
So
welcome.
that's pretty much it. We had a very, very amazing lecture today with you. Thank you so much for that. And thank you so much for answering all the questions. Thanks to all the participants who have joined us today. So
Thank you for having me again, and wishing you all good luck. And I really, really hope that, I mean, the women side, they go and progress much, much more than us, which they are already doing. And I
thank
would, like I said, even last time, I think when we had a meeting, uh, like usually one drawback for the women that I see is they go, they study a lot, they invest in their careers and everything. And once they get married, khalas. So yes, people say that the husbands are not allowing them to work. No, I don't agree on that. My wife, for example, I'm pushing her to she just finished her specialization in medical. She's a doctor, and I had to push her till the end. If I gave her a choice, don't do it, she'll sit and she'll not do it.
uh,
So this is what I don't like within the women of Pakistan, India, Bangladesh, that you people should actually, if someone is telling you to go study, do more, you should be actually happy. No, our women are not like that. They show that the husbands are not letting them, but no. For me, it's the other case. I have to push. I'll say, please, you're a brilliant student. Finish this, do this. So make sure that you guys do not waste all the efforts that you guys did to reach to a certain point, and then once you get married, you're like, ah, okay, I'll get kids, I'll settle down and finish. No, you have to find a way to settle between the family, the kids, and your career. Or why did you study? Is it just a badge? Is it just a nameplate? Is it just a piece of paper? Well, then I see that is a very wrong. So that is my opinion for the ladies or for the girls, that if you did something, please continue with it. Like husbands and men, we get married. Does it mean we leave our jobs? No. Or we will also say, I'm married, I have to give time to family, I stay home. No. So you
uh,
guys have to have that mentality. Yes, you have to run everything side by side and not leave your careers. Because if you leave it, I see a lot of doctors who, after marriage, they just sit at homes, which is a waste of, first, money of their parents, second, talent, third, space. Maybe that student who did a medical and she's sitting at home, someone else could have done it instead of her, who would have been working. So this is also something that you have to see. It's not just a name tag that I become an engineer, I become a doctor, I get married and khalas. No, that's not life. So this is
so
something I usually share with the girls, and even my students. Majority of my students in my department are girls. So I keep telling them this, that always keep pushing, have a meaning to your life. If you don't, life is not only about the kitchen and the kids and that's all. No, life is more than that.
thank you so much for sharing your thoughts on it.
Thank you, thank you.
I think
And no
Madhuri,
offense to anyone. Yeah, I'm just sharing what I am going through.
no. I totally agree with your thoughts. Thank you so much. So
You're
Madhuri
welcome.
wants to say something as
Yes,
well.
Madhuri. Madhuri, you have a question?
Sir, yeah,
Yeah.
sir. Good afternoon.
Good
Sir, I
afternoon,
work
Madhuri.
on IC engines,
Yeah.
fueled with biodiesel with MWCNT, multi-wall carbon nanotube.
Yeah.
So I found results that CO emissions are increasing when we add MWCNT for the biodiesel when filled with, I mean, for IC engines and CRD engines also. Does the same impact will be in air conditioning also, sir? Will it be
Uh,
having CO emissions?
the emissions are
I'm talking
increasing or
about CO.
decreasing?
The increasing, sir. But only for CO emission.
I
Carbon
think
oxide.
in the refrigerator, see, you have to look at the overall. By the end, when you get all the properties, for example, let's say you took
Yeah,
emissions
sir.
into account,
In
you took
actually,
heat
in
transfer, you took the, for example, in the refrigeration system, if we're doing, we have the COP. So if we take that into account, then by the end, you have to do a merit figure. Well, like for example, now in nanofluids, what we do is we do PEC value, PEC performance evaluation criteria. So the same you have to do in your case in the lubricants, or let's say nano refrigerants. If you see the overall performance criteria and you see that, let's say our value is 1, in nanofluids we want the value higher than 1 in overall, taking the pumping power, taking the viscosity, taking the negative impacts into account. If it is below 1, it means you should not be further investigating in that nanoparticle, for example, or that thing. Why? Because it's giving you a loss. The advantage is less compared to the uh, disadvantages. So that is always a criteria that we have to look into before we proceed into industry, for example. That's the reason why we do research in the lab scale, in order to decide whether this thing should go commercial or to industry or not.
okay.
Is that okay, Madhuri?
Yeah, yeah.
Thank you. Anything else? And another regarding the refrigerant, Madhuri, the problem is the one that we are investigating here. Hopefully, if we do it, it is already some refrigerant that is being not used around the world. The reason is because it's not environmentally friendly. But the company that we want to work with, probably they want to invest in this, and with time they are going to replace it. So yes, that is also going to calculate or affect a lot on reducing the emissions.
I think there are no more questions. You are very kind that you have kindly responded to all the questions very briefly. Thank you so much for the interactive session. And thank you so much the participants who have asked the
Thank you everyone, and assalamu alaikum.
Allah Hafiz.
Allah Hafiz.